When a hotkey expires, 100 workers can launch the same expensive LLM call. Redis single-flight locking turns that Stampede into one refresh. You'll learn how the pieces fit into a workflow that refreshes one missing answer and shares it across waiting callers. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Caches save repeated work, but they can turn into a coordination headache for LLM calls. Picture many workers asking the same question, the cache empty, and each one sitting on a slow model call. That multiplies cost and latency. We want just one worker to do the refresh and let everyone else reuse that result. Redis fits well. It's fast, shared, and it gives you tiny atomic ops so workers can coordinate cheaply. Here's the flow. Check Redis for an answer. If it's missing, try to become the single refresher by taking a short lock. If you win, call the model, write the answer with the TTL, and release the lock. If you lose, pull the cache until the value appears. Add jitter to expirations so keys don't all drop at once. Those moves reduce concurrent provider calls to 1 and keep latency predictable. We'll build a small demo. Open a Redis client, show a cache-aside write, add a safe lock release, apply jittered TTLs, and run a few threads to prove the Stampede is avoided. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, open a Redis connection so every worker can coordinate. This snippet opens the smallest useful Redis connection for the tutorial. A Stampede fix only helps if every worker can coordinate through the same shared system. So R is the redis-py client we will reuse across the later steps. Decode responses equals true keeps values as Python strings, which makes the cache examples easier to read on screen. The visible output shows Redis is reachable before we depend on it for caching and locking. Next, try a cache-aside miss and write the provider response into Redis. This example performs one cache-aside miss and stores the refreshed LLM-style answer in Redis. The pane starts with r.get returning nothing, because every worker that sees that miss might call the provider. Here answer is a compact stand-in for the provider response. Then r.set key answer ex equals 60 writes it with an expiration. A higher x reduces provider calls but can keep stale responses longer. A lower x refreshes more often but raises Stampede pressure. The visible output shows the value that would be served and cached after the first miss. To avoid many providers being called at once, add a single-flight style lock using Redis. This code lets several workers compete, but only one becomes the cache refresher. The r.set lock token nx equals true, ex equals 5 call is the single-flight gate. Redis accepts the first token and rejects the rest while the lock exists. The small Lua script passed to r.eval deletes the lock only if the stored token still matches, which avoids one worker accidentally releasing another worker's newer lock. The 5-second X is a guardrail against a stuck refresher holding the key forever. The visible output shows the selected owner and confirms the owner released its lock. Next, smooth expirations so related keys do not all expire together. This snippet spreads expirations across nearby seconds instead of letting related hotkeys all expire together. Random.seed 7 keeps the demo stable, while titles adds a small random offset to the base lifetime before each r.set x equals title. In production, the jitter range should be big enough to smooth refresh bursts, but not so big that freshness becomes unpredictable for your app. The Redis RTTL calls read back the remaining lifetimes, so the effect is visible. The output shows a real spread between cached keys, which helps reduce synchronized misses. Finally, run a small concurrent test that pulls everything together. This code turns the pieces into a tiny concurrent baseline for LLM cache stampede prevention. 6 threads call cached at the same time after R delete key lock creates a cold start. The first thread that wins R set lock 1 nx true ex5 runs provider, writes the refreshed value with R set key val ex60 and releases the lock. The other threads poll Redis until the value appears. Provider is a short teaching stand-in for a real model API call. The visible output shows one provider call and one shared value, which is the cost and latency win we wanted. You can map this toy demo to a real chat service. Replace provider with your actual LLM call. Size the thread pool to match your app concurrency, and use the same lock and TTL pattern in each service instance. The same Redis instance can coordinate hundreds of processes and keep model requests under control with minimal code. It's a shared cache pattern that funnels a miss to a single refresher. Use it when many clients or workers can trigger the same expensive model call. Watch the lock expiry and TTL choices. A lock that's too short can allow 2 refreshers, and one that's too long can block progress if a worker crashes. Try tuning the cache TTL of 60 seconds and the lock expiration of 5 seconds to match your provider latency and traffic patterns. And widen your jitter window so expirations do not line up under load. Measuring your real request latency distribution while you adjust those values will show the best trade-offs. If practical, hands-on AI engineering helps you. Subscribe and watch the AI engineering videos.